So today we are going to learn about maximum power transfer theorem. It is an extension to the Norton theorem which we have already covered. So you are familiarized with this circuit where on this side it is an equivalent circuit with Thevenin voltage and Thevenin resistance, and on the other side it is the load resistance across AB. So the maximum power transfer theorem says that across load AB, across load RL, the power is said to be maximum when your RL is equal to RTH. So it's said that the load resistance, when it's equal to the Thevenin resistance, we get the maximum power across the load. Okay, and it is calculated by P max is equal to V Thevenin the whole square upon 4 R Thevenin resistance. Okay, so this is basically the equations derived from the theorem, and we are going to use these equations to solve our problems. Now, just to get the glimpse of about how it came, we can go through some simple calculations where we know that our power is nothing but I square R. Okay, this is the general formula for power, and in this circuit it would be something P is equal to VTH, our voltage, upon RL plus RTH, okay, the whole square, because I am just substituting by I with this 2, and into RL, across which we are going to find the power. Now, we know a basic concept of calculus that if we take a differentiation of any element and we equate it to 0, then we can get the maximum of that element. So the same concept applies over here. If we want maximum power, we can set it as differentiating this power with respect to load resistance and equalizing it to 0. To get a more accurate glimpse, we can just do it graphically, that for the load resistance RL and for the power, if we take a differentiation and we want the maximum of it, then this would be the maximum, and this is basically a point when the differentiation is equal to 0, that is dP upon dRL is equal to 0. Okay, using this concept and this equation, if we put the value of P in this, then we get a situation where RL becomes equal to RTH. Okay, and this proves that this RL is equal to RTH, proves that this big equation becomes real, and this is basically the maximum power. Okay, so it says P max condition, it sets the P max condition where RL is equal to RTH. So now we have the condition and we have the formula for P. Just substitute the RL to RTH, we get the equation called P max equal to VTH upon 4 RTH. So this was a short derivation to the theorem, and we are just going to use these two formulas to get the solutions. So this derivation was just a small derivation to know how it came. Okay, so let's go with the examples. So this is a basic example. I have taken a small example over here, and the question would be in a form of at load RL, what would be the maximum power? Okay, and we just have to use the equations which we had derived back. It would be P max is equal to VTH square upon 4 RTH square. So for that we need to find VTH and RTH. So the main goal for any circuit would be to get an equivalent Thevenin voltage and Thevenin resistance, and then just substitute it to get the maximum power. Okay, so let's start with this circuit. I would first do the VTH. for VTH. So for VTH, we know that in a circuit, wherever there is a load resistance, we just get rid of it, and I'll just get rid of it, okay, and do the nodal analysis over here at points like, just let's take 1, 2, 3, okay. I'll start with point 2, because like over here at point V1 is equal to 100, okay, coming from this side. At this, I'll just consider it as V2, okay, and this would be my thing voltage, so I'll consider this as VTH, okay. So let's do the nodal analysis. It would be something for node 2, it would be my, I'll just take this as going out from everywhere, so it would be V2 minus V1, which is 100, upon my 4 ohms, plus at this point would be V2 minus 20, because it's 20 volt, so it's V2 minus 20 upon 4 again, plus V2 minus VTH, V2 minus VTH upon 4 is equal to 0. Okay, so solving this equation, we would get 3V2 minus VTH is equal to 120. Okay, I have solved it already, so I'm just writing it down as first equation, equation 1. Now at node 2, I'll write it down the second equation. It would be, for this it's going like this, let's assume going on this side, so it would be V2 minus VTH, V2, so at node 2, this one was node 1, so V2 minus VTH upon 4 plus going up, so it would be VTH minus Vx. So my Vx would be in this case V2 minus 20, agreed, because it would be just V2 minus 20. So at this resistance, it would be Vx, which is equal to V2 minus 20. So I just substitute it as V2 minus 20, okay, minus my 100, V1 going in because it's a dependent source, so I'm considering V1 as well, divide by the 4, which I know is equal to 0. Okay, at this point there is nothing. Okay, so at node 2, after calculating, I'll get the final equation as 2V2 plus 2VTH is equal to 80. Agreed. So this would be my second equation. Now solving this 2 equations, I can get my VTH is equal to solving this 2 simultaneous equations, I can get my VTH is equal to 20. Okay, this was part 1. I got my VTH. Now for getting RTH, I'll erase this now and do it for RTH. Okay, it goes with a similar is equal to 120. Okay, it goes a similar approach, so we are going to use the test source because there is a dependent source which we have. So at this point we are just giving a test source called VT. Okay, so, and the next thing would be for getting the equivalent resistance, the Thevenin equivalent. We know that every source, voltage source, becomes short, so this and this will become short, and then we just have to calculate using nodal analysis we can use any approach to get the Thevenin resistance. Okay, so I'll just use nodal analysis again, but this time we have no voltage sources, so it's just a short. Okay, so let's do it. Our first case will be like at node 2. Node 2, it would be V2 minus 0. So V2 upon 4 plus V2 upon 4 again. Yeah, it's V2 upon 4 plus V2 upon, at this side it's VT. So it's V2 minus VT upon 4 is equal to 0. Okay, this would be my first equation. Again, my second equation would be node at node 3 is equal to going this side, so it would be V2 minus VT upon 4, and going up would be my VT minus Vx, which is again V2 because there is no 20, so it's only V2 this time. So it would be plus Vt minus V2 upon 4, agreed, Vt minus V2 because Vx is equal to V2 now upon 4, plus at this point it would be I of t, like this is the voltage Vt and current across it is It, so it would be It upon, like nothing because we are just using the current, is equal to 0. Sorry, it's going inwards, so it would be minus It. Okay, now using 1 and 2, I can get V2 from this in terms of Vt, so I can get V2 in terms of Vt from this equation. I'll just put it over here to get an equation in a form of Vt and It. Okay, and that equation will look like something like Vt upon It is equal to 3. Okay, so if you do the calculations where V2, if you substitute if you get in terms of Vt and just put it over here, you will end up with a equation like Vt upon It is equal to 3, and when you get that, we know it's because it's Vt upon It, it is nothing but the RT, which is actually your RTh. Okay, so using these two equations, I got my RTh as RTh is equal to 3 ohms, and this was volts. Okay, now I just need to calculate my maximum power using the equation over here as equal to my 120 square upon 4 times 3 square. Okay, so 120 square upon 4 times 3 square, which will give me something around 1200 watts. Okay, so it's just the whole Thevenin theorem which we had, just substituted using the equation to get maximum power. That's it from